Okay, let's continue the work on homomorphisms, now with an example. So using the predicate h2, which says that something is an homomorphism from a two-argument operator to another one, we want to check if there exists any operator such that odd, the function checking if a number is even or odd, maps addition to this other operator. So does there exist any operator O cross such that h2 holds for odd, normal natural number addition, and this operator, which we want to find what it is, if it exists, and prove or disprove it. So let's start with adding the types. So odd takes any natural number to a Boolean. That means that to make the h2 predicate work, the addition here has to be on the natural number side, and the cross operator has to be on the Boolean side. And as you may remember, the idea here is that we translate from n to b, from n to b, and from n to b. So we translate both the arguments to the plus function and the result to Booleans. And we want to see if a sort of reduced form of addition is available on Booleans, which would make this property work out. So let's make a little more space by moving to the next slide, where I compacted these definitions a little bit. So here's the question then, what is h2? So we have to type out the definition just to see what we're doing. So if I write the whole proposition again, it says there exists an operator cross, and here I can be more specific and giving it the type that we inferred. There should exist such an operator, and then I expand the definition of h2. And h2 says odd of x plus y equals the cross operator of odd x and odd y. But as you might notice, there is something wrong with this expression. We have got an x and a y suddenly, which are not bound anywhere. So while this is the right shape, basically, of the proposition, it doesn't hold up completely. So let's move this expression down a bit and add the quantifications. So we need to, after the exists, add for all x and y of type natural numbers. So this is the complete expression. And looking again at the types, we have, let's make a blue color here. We have blue numbers x and y, and x plus y, and here also x and y. And then we have, let's also underline the type here. So the blue things here are the natural numbers. And then we have the translator, which goes from blue to green, the odd function. And then we have green types, and the result of applying odd to x and y. So the result here, the result here, the result here, and of course also the combined result. They are all Booleans. Okay, so now is the question, how do we go about proving this? And I think the first step in trying to prove it, or I mean, strictly speaking, still we're at the stage of prove or disprove. We want to explore if there exists an operator, what should it be doing? And as it turns out, there is actually not that many operators of this type, B to B to B, around. So it's a rather simple kind of operator. And let's move to the next slide, because there I've summed this up. So it turns out that a convenient notation for this operator is just a table with 4 boxes. So what are the 4 boxes? Well, it's what happens when I apply this operator to false or true as the first argument, and false or true for the second argument. So this is second argument, and this is first argument. Okay, so let's see now. We know how to compute odd and even numbers, so let's take some examples. If we have x equals 0 and y equals 0, then we can compute the different sub-expressions here. So x plus y is also 0, and odd of x plus y, well, 0 is not an odd number, so that is false. So then we can check what we got on the right-hand side. We got odd of 0, odd of 0. So in both these cases is false. So that means that we've computed here two values, which are the inputs to the cross operator, and one value, which is the output of the cross operator, because it should be equal here. So false and false are the inputs, and false should be output. So we can fill it in. So f here is the f we've computed was moved in there. Okay, so at least if this should work out, it always has to work out, but let's take a few examples first, just fill in the table. So with 0 and 0, we can fill in the upper left corner. Similarly, if we move to x equals 0 and y equals 1, then in a similar fashion, the left-hand side will be computed to odd of 1, which is then true, and that should be equal to odd of 0 plus odd of 1. But this is the same as false times true. Okay, that means with the first argument false, so the first argument false means the first row in this table, and the second argument true, the second column, it means the result to be filled in there is true. Okay, now we have 2 out of the 4 values, and here we are helped by the symmetry of addition, or the commutativity. So if we add two numbers x and y, or if we swap them around and add y to x, we get the same result. That means that we also force this operator to have the same property, because we move odd x and odd y to the opposite positions. Or actually this false and this true. So the same result, true, must hold also if we add up 1 and 0, which means we have to have true in this third box. So that was for this because of symmetry. So there is like a little yellow correspondence here. Whatever we put in those two boxes have to be the same, because our addition operator had this symmetry. Okay, in the final corner, what happens if both x and y are 1? So if x equals y equals 1, then we get to the case where odd x and odd y are both true. So that's the lower corner. And then we check what is odd of 1 plus 1. Well, that's odd of 2, which is false. 2 is not an odd number. So we can fill in the last component of the square, of the multiplication table as false. Okay, so now we computed with testing with 4 pairs of natural numbers, 0 and 1, into the 2 different combinations, and come to the conclusion that if there exists an operator, it must have this multiplication table. So now the remaining question is, does this work also for other numbers than 0 and 1? So here I had filled it in beforehand. Also, actually, I used 2 and 3 as the examples there. But I want to focus a little bit now on the image at the bottom of the screen. So we have mapped an infinite set of numbers, all the even numbers, to false as not being odd, and all the odd numbers to true. So in general, if we would do this, we take away all the information about the number except for the value of its least significant bit. So I mean, if we make the binary representation of the number, we can look at just one bit, and that's the oddness. If it's 1, then it's odd, and if it's 0, then it's even. And then when we compute this operator, the only thing it knows is if we ended up in this subset or this subset. So we don't know anymore if we came from 8 or 5 or 2 or whatever. We only know the result of odd. So it's definitely not obvious that this will work out. But as you might imagine, from what we learned probably in primary school somewhere, this actually does work out. So let's try to prove it. So first, let's see, what is the operators? I mean, we call it here the cross with a ring around it. But actually, if we look at what it actually does, we can recognize it as the XOR operation, exclusive OR. So it's true if the first or the second input is true, but not if both are true. So it also, another way of implementing it is noting that it's actually when the two inputs are not equal. But this is not necessary for a proof. It's just convenient that it's XOR. And it also, another way of viewing it is addition modulo 2. So 0 plus 0 is 0, 1 plus 0 is 1, but 1 plus 1 is 2, which modulo 2 becomes 0 again. So this modulo computation is the key to proving this. And here I've actually already written the proof, but let's see if we can talk our way through it. It's not a complicated proof, but I like to be rather careful here. So first of all, we know that every natural number can be written as an even number plus 0 or 1. So either the number is even, in which case b is 0, or the number is odd, in which case b is 1. So I'm already here trying to capture the evenness of the number. And the statement I've written here is a logical statement which summarizes this. So for every natural number, there exists a k, which is also a natural, and there exists a b, which is in the set I called z2. So often you have z and the subscript for the set of numbers from 0 up to 1 less than the subscript. So this is just a set of 0 and 1. And then I say, okay, for all n, there exists a k and a b such this equality holds. Okay, then I apply this to our input x, which is supplied to odd, and then we get a kx and a bx. I call them x with subscript here just to keep track of that there are two different of these, because I will also say that there exists ky and by such that y is equal to this even number plus the remaining bit. And then we can note that from things we know about odd numbers, if we add an even number to the odd number, it remains, I mean, the oddity of x is the same as the oddity of bx. The parity doesn't change if you remove an even number. And similarly, the oddity of y is the same as the oddity of by. And that means that if we're computing our way here towards this expression up on the right. We want to check this expression. We want to check if the oddness of the sum is related to the oddness of the two components combined. So we want the sum And here I've just done a simple algebraic manipulation using these two expressions. I collected the 2 times and the 2 bits. So by a similar reasoning as we had before, we know then that the oddity of the sum is the oddity of just this sum of the remainders, bx and by. Okay, what remains to prove here, as we now reduced the left-hand side of oddity of x and y to the oddity of just 2 numbers, each of which can have 2 possible values, that means we only need to check 4 cases. So these cases are almost the same as the cases we had previously. So if both bx and by are 0, then we know that we have false times false. That result, on the right-hand side, we will get false. So I'm trying to write here the equality, the instance of the equality up here. I'm putting that in the box. So the right-hand side is the result of applying it false, and then the left-hand side is whether or not the sum is odd. Well, if we sum up 0 and 0, we get 0, which is definitely not odd. So false, we want to check here if false is equal to false. Yes, it is. So if one of them is odd, then we actually get true equals true. Here we also can check that it's true equals true. And then in the final case, then we've got both the bits are 1. So 1 plus 1 is 2, but that is also not odd. So we get false equals false. So again, what I'm filled in here is this equality for the case where I've chosen bx to be 0, 0, 0, 1, and so on. And all of these 4 cases, which is the only thing remaining from the for all, remember we had a for all x for all y, but the for all x for all y is now for all bx and by, because that's the only thing remaining, and that's just 4 cases. So by checking the 4 cases, we've actually now proven that odd is indeed an homomorphism from addition to XOR. Okay, so strengthened by this positive example, let us try another example. Is the function is prime, so primality checking, is that function a homomorphism from addition to any operator? This is from the book, section 432. So we have this similar picture here. I can write down the types. So is prime is yet again from natural numbers to booleans. And that also means we have the same addition as before between natural numbers. And it means that the operator here, again, is of the same type. It's a very simple function. It only has 2 by 2, 4 different cases. And as we know, a view of this is prime function can be as separating the natural numbers into 2 sets. The lower set here, which is mapped to true, is a set of all prime numbers, 2, 3, 5, 7, and so on. And the upper part is the natural numbers which are mapped to false of the is prime predicate. And those are all the other natural numbers. So 2 infinite sets, and is prime is mapping them to just 1 out of 2 possible values, false or true. So now, how should we go about proving that there exists or there doesn't exist a function is prime? Well, let's look at some examples, as we did before. So if we if we assume that there is no such is prime, we can actually prove it and by checking these different examples. So if we assume that there is a function, a bool to bool to bool, which satisfies this property, then we can try to create values for which this is not sort of clearly not the case, and then from that we can conclude that it cannot be true. So I will do this by first defining a value b, which is this operator which we have assumed exists. Remember, it's just a normal Boolean function, but you can apply it to true and true, and then we get the result. It's either true or it's false, but it doesn't matter for the reasoning that comes. What matters is that it can only be one value. I mean, there exists an operator, and it defines a unique value b, which comes in if we send two truth values to it. And then we would like to find some kind of problem with this claim from this law. So we have assumed that this law holds for this operator, so let's try to provoke it a bit. So first we want to get this corner, to get to this bit, we want to have some numbers x and y which we know are prime. So our first easiest example is, let's take x equal y equal 2. So 2 is prime, which means that if we compute the right-hand side, I can write it below here, this becomes then is prime of 2 cross is prime of 2. And we know from that this requires now that this should be the same as is prime of 2 plus 2. So we're trying to check this, or rather we're trying to use this equality. It holds for all x and y, and let's see what it leads us, where it leads us. So if I put a little blue line in between here to separate the matters. So if you simplify this is prime of 4. And that should be the same as, well, is prime of 2 is true. And this is prime of 2 again, which is also true. So this right-hand side is actually the b we've defined. Okay, we don't yet know what it is, but looking at the left-hand side, is p 4? Well, we do know what that is. That is equal to false. So, okay, we've now come to the conclusions. So this so far means that b must be false. Okay, fine. I mean, there is nothing strange with saying that the operator should return false, giving two truths. After all, that was the case in the odd function. But let's check with some other numbers to see if this is fishy. So the next example, we want to find another variant where the primeness is the same. So I will now use, for the second example, I will say, okay, let's take x bar, which is a variant here, and I will make that 3. And I'll keep y equals 2. Okay, and then I will just copy down this expression with those values inserted. Well, actually, the expression where I use x bar instead. So we know now that is prime of 3 plus 2 is equal to is prime of 3, and this operator, and that is prime of 2. Well, as we've chosen this number to be mapped to the same as 2, so both are actually primes, so both are mapped to true, we will actually get on the right-hand side here, true cross true, which again is our b. I mean, we defined b over here to be true cross true. But now something disconcerting has happened on the left-hand side, because this is prime of 5, and I'm not writing a very clear notation here, so this is prime of 5, which is, well, 5 is prime, so this is now true. So now we've proven that b equals true. I mean, we have b over here and we have true there. And these two statements, b equals false and b equals true, both follow from assuming that an operator exists without saying anything about which value it has. We just called it b. And then checking, as we know, it should hold, the assumption is it should hold for all x and y. We need to check only for two pairs of values, for x equal y equals 2, and for x bar equals 3 and y equals 2. And we got contradictory results, which means the assumption was wrong. If the assumption that it exists was wrong, it means it doesn't exist. So the thing we can conclude here is no. I mean, does there exist? No. No cross exists with this property. So there are lots of operators on Booleans, well, actually not that many of them, but whatever we put there, is prime cannot possibly be satisfied that it takes an addition to this. And of course, if it would be possible, then we would have a very easy job of doing prime checking, but we don't. So if you just sum up the notes before, the key here was to get to a contradiction from identifying a few cases, the primeness of 2, the primeness of 3, and then the 2 plus 2 and 2 plus 3 being 4 and 5, and saying that even though these two map to the same value, the sums were mapped to different values. So remember, in a sense, what the homomorphism condition is saying is that any equality of this shape should be mapped to an equality on the other end. So we map the primeness of 2 to true, the primeness of 2 to true, the primeness of 4 to false, primeness of 2 and 3 and 5 to true, true, true. And then, even though we don't know what the operator is, we do know it's a function, and functions only have one possible out value. It can't have different values for the same inputs. So this is definitely a contradiction, and no such operator can exist. And this is a simple case. As I mentioned, it's also in the book. You have a slightly more advanced example of it, part of, if you're taking the course, the assignment 2, the second lab that you need to hand in, where you need to prove that something is not a homomorphism. So this is the proof method I would recommend. Okay, yes, and that was all for this. I will continue with a demo with the live coding.